The date is March 1944, a factory floor in Detroit. The noise is deafening, metal screaming against metal, welding torches hissing, massive steel plates being moved by cranes overhead. In the middle of this industrial chaos stands a man named Thomas Blandings, a welder, 42 years old, hands scarred from years of work, eyes protected by dark goggles. He's staring at a Sherman tank hull that failed inspection. Again. The weld cracked under stress testing. Again. And somewhere in France, men are dying in tanks just like this one because the armor isn't holding together the way it should. Blandings has an idea. It's been forming in his mind for weeks, keeping him awake at night. It's so simple that it feels stupid. So obvious that surely someone smarter, someone with an engineering degree, someone who actually matters, must have already thought of it and dismissed it. But the idea won't leave him alone. He's thinking about his house, specifically about how his house is built, about the nails that hold the wooden frame together, about how those nails don't just sit on the surface, they penetrate, they go through. What if armor worked the same way? Right now, understand what you're looking at when you look at a Sherman tank in 1944. You're looking at multiple plates of steel welded together at the seams. Thick steel? Sure. Good steel. American steel. But here's the problem. When a shell hits near a welded seam, the weld itself becomes the weak point. The weld is where two separate pieces of metal are joined by melted metal. It's strong, but it's not the same as the plate itself. It's a scar, a seam, a place where the armor is fundamentally different from the surrounding material. Engineers knew this. Of course they knew this. They'd spent years perfecting welding techniques, adjusting temperatures, testing alloys for the weld material. They'd made the welds as strong as metallurgy allowed. But they were still welds, still seams, still the place where tanks came apart under fire. Blandings looks at that failed hull and thinks about nails. He thinks about how a nail driven through two pieces of wood doesn't just connect them at the surface. It creates a mechanical bond that goes through the material. He thinks about how you can't pull two boards apart without either pulling the nail out or breaking the wood itself. The connection is physical, structural, deeper than surface contact. What if you could do that with armor plate? He approaches his supervisor the next day. The supervisor is a man named Dutch Hendricks, a former pipe fitter who worked his way up to floor management. Hendricks is tired. Everyone is tired. They're producing tanks at a rate that would have seemed impossible 2 years ago, and it's still not enough. Every week brings new demands, new quotas, new pressure from Washington. The last thing Hendricks needs is a welder with an idea. But Blandings is persistent. He explains it during a lunch break, drawing on a piece of paper with a grease pencil. What if, before you welded the seams, you drilled holes through both plates where they overlap? What if you put steel pins through those holes? Big pins, strong pins, like nails, but made of hardened steel. Then you weld over everything like normal. Now the plates are connected in two ways, by the weld on the surface and by these pins going through the thickness of the armor. If the weld cracks, the pins still hold the plates together. If a shell hits the seam, the impact force is distributed through the pins into both plates, not just stressing the weld. Hendricks stares at the drawing. He's thinking about production time, about how many extra steps this would add, about how much it would cost, about how he'd have to explain this to his boss, who would have to explain it to his boss, and so on up a chain of command that disappears into Washington. He's thinking about how many times someone has come to him with an idea that sounded good on paper and failed in practice. But he's also thinking about the cracked hull 20 feet away. He's thinking about a letter he received last month from his nephew, a tank commander in Italy, who described what happens when a Panzer round hits a Sherman just right. How the weld seams split, how the armor comes apart, how the interior becomes a place where metal fragments move faster than sound. Hendricks tells Blandings to build a prototype, just one, on his own time. If it works in testing, they'll talk about it. If it doesn't, they never had this conversation. This is where the story should become simple. Man has idea. Idea works. Idea gets implemented. But that's not what happens. Because what Blandings is proposing, without fully understanding it, is a challenge to something more fundamental than engineering specifications. He's challenging the certainty of experts. He's challenging the established methods that have been refined over years of work by people with degrees and titles and authority. He's suggesting that maybe the smartest people in American metallurgy missed something that a welder noticed while thinking about carpentry. That kind of challenge doesn't get accepted easily. Not because people are stupid or malicious, because accepting it means confronting an uncomfortable possibility. That expertise isn't the same as omniscience. That formal training can create blind spots. That sometimes the solution is obvious only to someone who doesn't know enough to understand why it shouldn't work. Blandings spends 3 weeks building his prototype in a corner of the factory after his shift ends. He's using scrap metal, rejected plates that failed inspection for minor flaws. He drills holes. He fabricates pins from hardened steel stock. He positions them at intervals along what would be the weld seams. Then he welds everything together, the pins now embedded in the weld, creating mechanical connections through the thickness of the armor. The test happens on a Saturday morning. A small group gathers. Hendricks, 2 quality control inspectors, an engineer from the Army Ordnance Department who happened to be visiting the factory. They subject the test piece to the same stress testing that caused the standard welds to fail. Hydraulic pressure, impact testing, extreme temperature cycling to simulate combat conditions. The welds hold. Not perfectly, nothing is perfect, but they hold significantly better than standard welds. When they finally do crack under stress that would have catastrophically failed a normal seam, the pins keep the plates mechanically connected. The armor doesn't come apart. It stays structural. The engineer from Ordnance, a man named Captain Robert Wesley, asks the question that everyone is thinking, why didn't we think of this before? It's such a simple concept. Mechanical fastening plus welding. Belt and suspenders. Basic redundancy. Why did it take a welder's informal experiment to discover something that should have been obvious to metallurgical engineers? The answer is complicated and uncomfortable. It involves the way expertise develops, the way training focuses on refining known methods rather than questioning underlying assumptions, the way institutional momentum makes it easier to improve existing solutions than to imagine different approaches. Wesley, to his credit, doesn't dismiss these thoughts. He writes them in his report, though he knows they'll make people defensive. But here's where the story gets harder. Because now they have to decide what to do with this information. They have a method that appears to significantly improve armor integrity. But implementing it across Sherman production means retraining workers at multiple factories, redesigning production workflows, creating new equipment specifications for the pins, testing extensively to determine optimal pin placement, size, and spacing, slowing production temporarily while the changes are implemented, and most difficult, admitting to the field that tanks already delivered have a flaw that could have been prevented. The meetings that follow happen in rooms Blandings never enters. Officers and engineers and production managers reviewing data, conducting more tests, arguing about timelines and costs and logistics. Some argue for immediate implementation. The improvement is real and significant. Every week of delay means more tanks with inferior armor going to men who need the best protection available. Others argue for caution. Rushing changes causes mistakes. Better to test thoroughly and implement correctly than to create new problems trying to fix old ones. What Blandings doesn't see, sitting at his welding station wondering if anyone will even tell him what they decided, is the deeper argument happening in those meetings. It's not really about pins and welds, it's about certainty, about the fact that the armor they'd been producing and testing and approving was based on years of expert analysis and still turned out to be not as good as it could have been, about what else might be wrong that they haven't noticed yet, about the gap between what they think they know and what's actually true. This is the part where we need to understand something about how knowledge works in systems, especially in wartime. Everyone involved in Sherman production was competent, more than competent, brilliant in many cases. Metallurgists who understood stress and strain at a molecular level, engineers who could calculate load tolerances in their sleep, factory managers who coordinated production with remarkable efficiency. These weren't fools missing obvious solutions. These were experts operating at the peak of their fields. But expertise comes with blinders. When you've spent years learning the right way to do something, your brain stops considering whether there might be a different way. Not because you're arrogant, because mental resources are finite. You can't question every assumption every time. You have to take some things as settled, so you can focus on the unsettled questions. The problem is that sometimes the settled questions aren't as settled as you think. Blandings didn't have those blinders, not because he was smarter, because he didn't know enough to have developed them yet. He looked at armor plates and saw boards. He looked at welds and saw glue. He brought a carpenter's intuition to a metallurgist's problem, and the collision of those perspectives created a solution that neither could have found alone. In late April 1944, the decision comes down. Implement the pinning method on all new Sherman production. They're calling them shear pins now, a proper technical name for Blandings nails. Engineering teams determined the specifications: 3/4-inch diameter hardened steel pins, placed at 8-inch intervals along all major weld seams, extending through the full thickness of the overlapping plates. They run extensive tests. They measure improvements in weld integrity, in impact resistance, in the tank's ability to maintain structural coherence under combat damage. The numbers are striking. Armor sections with shear pins show approximately 47% better resistance to weld separation under stress. Tanks that take hits near seams maintain structural integrity where pre-pinning tanks would have suffered catastrophic weld failures. It's not making the armor thicker or stronger in terms of raw penetration resistance. It's making the armor stay together when it gets hit, which in practice turns out to be just as important. They bring Blandings to one of the meetings, not to the high-level policy discussions, but to a technical review where they need him to explain his thinking to engineers who will write the formal specifications. He sits in a room with men who have degrees he can't pronounce from universities he's only heard of, and he explains his idea with the same grease pencil on paper that he used with Hendricks. The engineers ask good questions about thermal, expansion differentials between the pins and plates, about whether the pins could create stress concentration points, about galvanic corrosion, about a dozen technical considerations that never occurred to Blandings. He doesn't have answers to most of their questions. That's not his job. His job was having the idea. Their job is making it work properly. But there's a moment near the end of the meeting where one of the engineers, a man named Dr. Paul Chernoff from MIT, asks Blandings a different question. He asks, "How did you think of this? What made you look at an armor plate and see something different than what we saw?" Blandings thinks about it. He talks about his house, about watching it being built when he was young, about understanding that connection isn't just about surface contact, about how the strongest joints are the ones that go through the material, not just across it. He talks about not knowing enough about metallurgy to understand why it shouldn't work, so he just thought about whether it could work. Chernoff writes something in his notebook. Later, he'll include it in a paper on engineering methodology. He'll argue that optimization of existing solutions can blind you to alternative approaches, that sometimes the most significant innovations come from outside the expert consensus precisely because the outsider doesn't know what's supposed to be impossible. He'll use Blandings and the shear pins as a case study. The paper will be read by engineering students for decades. But that's future. Right now, in May 1944, factories are retooling. Workers are learning the new process. The first Sherman tanks with shear pin armor are rolling off production lines. They're being loaded onto ships bound for Europe, where the Allied invasion of France is weeks away. The men who will crew these tanks don't know about Blandings. They don't know about the meetings or the debates or the decision process. They just know that their tank is supposed to be tougher than earlier models. They trust that somewhere, people smarter than them made it as safe as possible. Some of those men will survive hits that would have killed crews in earlier Shermans. The armor will hold together under damage that would have caused catastrophic weld failures in unpinned tanks. They'll climb out of wrecked vehicles that stayed structurally intact enough to protect them. They'll never know why. They'll never hear the name Thomas Blandings. They'll just live, which is what matters. But there's another side to this story, and it's darker. Because while new tanks are getting the improved armor, thousands of Shermans already in service don't have it. Can't get it, not easily. Retrofitting would mean pulling tanks out of service, shipping them back to depots, disassembling armor sections, drilling and pinning and re-welding. The time and logistics are prohibitive. So a decision is made. New production gets the pins, existing tanks continue as they are. This means that for months, two kinds of Shermans are in service simultaneously, some with shear pins, some without. The men inside can't tell which kind they have. There's no external marking, no way to know, and nobody tells them. Not because of malice, because information control is tight and the differences are technical, and explaining would require admitting that earlier tanks were less safe than they could have been. Think about what that means. You're a tank commander in France, July 1944. Your Sherman takes a hit. The weld seams hold. You survive. Is that because you have the improved armor, or because you got lucky? Your friend in the next tank over takes a similar hit. The welds fail. He doesn't survive. Is that because he had old armor, or because his hit was worse, or because randomness and chaos make every combat situation unique? You never know. You can't know. The information exists somewhere in procurement records and serial numbers and production logs, but not in any form accessible to you. So you live or die based on variables you can't see, can't control, can't even verify after the fact. This is what Blandings thinks about at night, the part that troubles him more than the question of credit or recognition. His idea is saving lives. He knows that. But it's not saving all the lives it could save because implementation is slow and partial and constrained by the realities of wartime production. There are men dying in tanks that could have been made safer, not through technology that doesn't exist yet, through a simple modification that a welder thought of while thinking about carpentry. How do you live with that? With knowing you discovered something important, but the gap between discovery and full implementation creates a window where people die preventably? Blandings doesn't have an answer. Nobody does. It's the mathematics of industrial war. Improvements roll out incrementally while the killing continues constantly. By September 1944, most new Sherman production includes shear pins. By December, virtually all new tanks have them. Retrofit programs begin for tanks in rear areas, though frontline vehicles mostly continue as is because pulling them out of service is tactically unacceptable. By the time the war in Europe ends in May 1945, the majority of Shermans in service have the improved armor, though thousands never get the modification. Post-war analysis will attempt to quantify the impact. They'll look at tanks with shear pin armor versus those without. They'll measure survival rates, weld failure rates, structural integrity under comparable damage. The data is messy because combat is messy. Tanks get hit in different places at different angles with different munitions under different circumstances. But the overall pattern is clear. Shear pins significantly improve the Sherman's ability to maintain structural integrity under combat damage. Best estimates suggest the modification prevented several hundred catastrophic armor failures over the last year of the war in Europe. Several hundred. That's not thousands. It's not a miracle innovation that transformed the Sherman into an invincible vehicle. It's an incremental improvement that made a good tank somewhat better. But several hundred armor failures prevented means several hundred crews that had better chances of survival. If you're in one of those crews, the improvement isn't incremental, it's everything. Blandings receives a commendation letter from the War Department. It's formal and bureaucratic, and mentions his contribution to armor development without going into detail. His name appears in a few technical reports filed away in military archives. Some engineering journals publish articles about shear pin armor without mentioning him at all, treating it as an obvious application of known principles. The knowledge becomes absorbed into standard practice, the way useful ideas do, until nobody remembers it was ever new or controversial or derived from a welder thinking about how houses are built. He goes back to welding. The war ends. The factory shifts to peacetime production. Blandings works there for another 18 years before retiring. He tells the story sometimes about the idea and the tests and the meetings. His grandchildren listen politely and don't fully understand why it matters. It's a story about tanks and welding, technical and distant, not obviously connected to their lives. But here's what the story is really about. It's about the gap between expertise and truth, about how the people who know the most about a subject can miss things that outsiders notice precisely because they know so much, about how optimization makes you better at the current approach while potentially blinding you to different approaches, about how certainty, even well-earned certainty, based on years of study and practice, can become a liability when it stops you from questioning basic assumptions. The experts who designed Sherman armor were brilliant. They understood metallurgy and stress analysis and manufacturing processes at levels Blandings never approached, but their expertise existed within a framework, a set of assumptions about how armor should be constructed and connected. Welding was the right answer within that framework. The question was how to make better welds, not whether welding alone was sufficient. Blandings asked a different question. What if the connection needs to be more than surface joining? Not because he knew something the experts didn't, because he didn't know enough to stay within their framework. His ignorance was liberating. It let him imagine solutions that violated the implicit assumptions that experts didn't realize they were making. This pattern appears throughout the history of innovation. Outsiders contribute breakthrough ideas, not despite their lack of expertise, but sometimes because of it. They're not constrained by the knowledge of what shouldn't work. They don't know that their idea is supposed to be impossible or impractical or already tried and dismissed. They just see a problem and imagine a solution, free from the weight of established wisdom. But notice the other side of this pattern. Blandings couldn't implement his idea alone. He needed experts to test it properly, to understand the metallurgical implications, to design the specifications that would make it work reliably at scale. The breakthrough came from outside expertise. The implementation required deep expertise. Both were necessary. Neither was sufficient alone. This is the tension that exists in every complex system. You need experts because real problems require deep knowledge. But you need to create space for non-experts to challenge expert consensus because expertise creates blind spots. You need established wisdom because not everything needs to be questioned constantly. But you need to remain open to the possibility that established wisdom is wrong because it sometimes is. You need confidence in your knowledge because paralyzed by doubt, you can't act. But you need humility about your knowledge because overconfidence kills. There's no clean resolution to this tension. You can't optimize it away. You can only navigate it case by case, trying to be both confident and humble, both knowledgeable and open to challenge. Most of the time you'll get it wrong in one direction or the other. Sometimes you'll reject good ideas because they contradict expert consensus. Sometimes you'll waste time on bad ideas because you gave too much credence to uninformed challenges. The best you can do is try to learn from mistakes and adjust, knowing you'll make different mistakes next time. The men who approved shear pin armor faced this tension directly. They had to decide whether to trust the established methods that experts had refined over years, or to gamble on an untested idea from a welder with no formal training in metallurgy. The data helped. The test results were compelling. But data doesn't make decisions. People do. And the decision required acknowledging that maybe the experts had missed something. Maybe the established approach wasn't optimal. Maybe a different framework revealed possibilities that the expert framework obscured. They made the right choice ultimately, but understand how easily they could have made the wrong one. How reasonable it would have been to dismiss Blandings' idea as naive, as a misunderstanding of metallurgical principles, as an impractical complication of established manufacturing processes. How many good ideas probably were dismissed exactly that way, by reasonable people making defensible decisions based on expert consensus. This is what keeps you awake if you think about it too much. The knowledge that reality is more complex than any framework for understanding it, that your certainty is always partial, your knowledge always incomplete, your expertise always bounded by assumptions you don't realize you're making. That somewhere, right now, someone without credentials is seeing something you're missing, and you'll probably dismiss them because you know better, and sometimes you'll be right, but sometimes you'll be wrong, and people will die because of choices made in good faith based on incomplete understanding. Blandings understood this better than most, not because he was philosophical or introspective, but because he lived it. He saw the gap between his simple idea and the complex reality of implementation. He saw experts take his insight and transform it into something he couldn't have created alone. He saw the slow grind of institutional process, necessary and frustrating in equal measure. He saw the distance between discovery and deployment and the human cost accumulated in that distance. And he saw something else in the decades after the war when the story faded into historical footnote. He saw how easily innovation becomes normalized, how the breakthrough idea becomes standard practice, becomes obvious, common sense becomes how we've always done it, how the struggle to change minds gets forgotten once the change is accepted, how each generation inherits solutions and forgets they were once controversial proposals that reasonable people rejected. This is maybe the deepest lesson, that your certainty today is built on forgotten battles over ideas that seemed crazy until they worked. That your common sense is the residue of someone else's breakthrough. That your expertise, however hard-earned, incorporates assumptions that will seem naive to future experts who see what you're missing. That certainty is always temporary, always partial, always one good idea away from obsolescence. In 1962, Blandings retired from factory work. He spent his retirement building furniture, good solid pieces made with traditional joinery, mortise and tenon, dovetails, and yes, nails where appropriate. His grandchildren remember him as meticulous, patient, someone who understood that good work requires attention to how things connect. They didn't know he'd applied that same understanding to tank armor. It never came up. He died in 1979, age 77. The obituary in the local paper mentioned his 40-year career in manufacturing, his service in the community, his surviving family. It didn't mention Sherman tanks or shear pins or the hundreds of men who lived because a welder thought about carpentry. That information existed only in technical documents and military archives, disconnected from the man who originated the idea. This is how history works. The big names get remembered, the famous battles and dramatic moments, the generals and politicians. But underneath, invisible in the official narratives, are thousands of small decisions made by unremarkable people facing ordinary problems. A welder noticing that armor seams fail, a supervisor willing to listen, an engineer humble enough to test an idea that challenged his expertise, a procurement officer who pushed for rapid implementation despite institutional inertia, each decision small, each person unimportant in the grand narrative. But aggregate those thousands of small decisions and you get outcomes, battles won or lost, lives saved or wasted, technologies that succeed or fail. The grand narrative is built from countless invisible choices made by people whose names never enter the history books. Blanding's contribution was real and significant, but it was also representative of a larger pattern. Everywhere, constantly, ordinary people solving ordinary problems in ways that incrementally improve or worsen the systems they're part of. The question is whether those systems create space for good ideas to emerge and spread. Whether they're structured to hear challenges from unexpected sources, whether they balance confidence with humility, expertise with openness, established wisdom with willingness to reconsider, whether they fail gracefully by catching mistakes before they become catastrophic, whether they learn and adapt or calcify and repeat. Sherman tanks with sheer pin armor worked better than those without. That's measurable. But the deeper question is why it took a welder's informal experiment to discover that improvement, why the formal design process, with all its expertise and resources, missed something so relatively simple, what that reveals about the blind spots inherent in expert systems, and what it suggests about how many other improvements remain undiscovered because the people who might notice them don't have the credentials to be heard, or the confidence to speak up, or the access to decision-makers who could test their ideas. You can't answer these questions with certainty, but you can hold them. You can let them inform how you think about expertise and innovation and institutional decision-making. You can try to build systems that capture good ideas from unexpected sources while filtering out the vastly more numerous bad ideas that also come from unexpected sources. You can try to remain humble about what you know while confident enough to act on it. You can try to hear challenges to your expertise without being paralyzed by constant doubt. Mostly, you'll fail. Everyone does. But occasionally, in the gap between certainty and doubt, between expertise and ignorance, between established wisdom and fresh perspective, you'll find something true that you'd been missing. And if you're lucky, if the system works, if the timing is right, that truth will spread. It will save lives. It will improve outcomes. It will become the new established wisdom that future innovators will have to challenge when they notice what it's missing. The Sherman tanks are gone now, mostly, scrapped or donated to museums or rusting in forgotten surplus yards. The men who crewed them are mostly gone, too. The welders and engineers and procurement officers, the whole apparatus of wartime production dismantled and transformed. But the pattern remains. The tension between expertise and innovation, the question of how to know what you don't know, the gap between discovery and implementation, the human cost of that gap. These aren't historical questions, they're current ones. Right now, in systems you're part of, expertise is missing things that outsiders might notice. Established methods are producing suboptimal outcomes that alternative approaches might improve. Certainty is preventing inquiry. Institutional momentum is preventing change. And somewhere, maybe someone without credentials, has an idea that could matter, if anyone was structured to listen. You can dismiss this as speculation. But Blandings' story proves it's not. The pattern is real. It happens. The only question is whether you're on the side that notices or the side that dismisses. Whether you're Blandings, seeing the armor plates differently, or the first engineer who looked at his drawing and thought, that's too simple to work. Whether you're Hendricks, willing to authorize a test, or the manager who would have said no. Whether you're the system that adapts or the system that ossifies. Most of the time, you won't know which you are until afterward, until the test results come back, until the decision proves right or wrong, until the alternative timeline where you chose differently plays out in imagination, and you wonder whether those people would have lived if you'd listened or died if you'd changed what didn't need changing. This uncertainty is uncomfortable. It's supposed to be. It's the cost of operating in complex systems where knowledge is partial and consequences are real. The comfort is that you don't have to be right every time. Blandings wasn't right about everything. Most of his ideas probably didn't work. We only know about the one that did. The system doesn't require perfection. It requires enough openness that good ideas can occasionally get through, enough testing that bad ideas get filtered, enough humility that certainty doesn't become rigidity, enough confidence that doubt doesn't become paralysis. Somewhere in that balance, messy and imperfect, and constantly adjusting, innovation happens. Lives get saved, systems improve, knowledge expands, not through genius breakthroughs by exceptional people, but through incremental contributions from ordinary people who notice small things and speak up and get heard. Most contributions don't matter much, but some do, and you don't know which until you try. That's the real lesson of the shear pins. Not that welders are secretly smarter than engineers, not that expertise should be distrusted, but that complex problems require diverse perspectives, that certainty should be provisional, that established wisdom should be questionable, and that the gap between what we know and what's true is always larger than we think. Stay humble, stay curious, stay open. Question your certainty, test your assumptions, listen to unlikely sources. And when someone shows you a better way, even if it comes from an unexpected place, have the courage to admit you missed it. Because somewhere, right now, armor is failing, not tank armor, metaphorical armor. Systems and methods and established practices that work mostly, but not optimally. And somewhere, someone without credentials is noticing. They're thinking about it. They're wondering if there's a better way. The question is whether they speak up, whether anyone listens, whether the idea gets tested, whether it spreads. The question is whether your system is one that would have implemented shear pins or one that would have dismissed them. Whether you're building the next generation of better solutions or calcifying around the current generation. Whether you're learning from blandings or repeating the mistakes that made his contribution necessary. You won't know until the moment comes. But when it does, remember the welder who thought about nails. Remember that certainty is dangerous. Remember that expertise has blind spots. Remember that better answers sometimes come from unexpected places. Remember that the gap between discovery and implementation measures itself in lives. And choose accordingly, knowing you might be wrong, but that choosing nothing is also a choice, with its own consequences, its own costs, its own answer, to the question of whether this system, this moment, this decision, will be remembered as the one that listened or the one that dismissed the voice that happened to be right.